Hi, I'm Veikka, and this is my master's thesis results presentation. My topic was on diagnosing and improving a churn prediction model. So, some background first. Churn is the event when a customer cancels their subscription or contract of a service. And then churn prediction is a very common application of machine learning where you attempt to predict who cancels their contract based on some given features. And then the output can be binary label or perhaps more commonly a probability of churn. And then the motivation for churn prediction is first of all monetary. It's a known fact that keeping existing customers is cheaper than acquiring new ones. Then also when you identify these risky clients or contracts, you can perform focused retention efforts. It's cheaper than to do a campaign for all the clients at once. And then through this analysis, you can also uncover reasons behind churn for your company or product as well. I did the thesis for this Finnish equipment manufacturing company that operates globally. They sell maintenance contracts for their equipment, and then the goal here is to predict the probability of such a maintenance contract churning. They do have an existing model. It's the result of 10 years of incremental development by different teams and different people. And in the last year, it also overwent a large technical migration with a priority in development speed. So there has not been a proper validation of the approach and methods in a very long time. And the current situation with the model is that the predictions are not reliable. They're underutilized in the end users, who are the sales teams of the company, and the predictions accuracy is basically slightly above random classification. And for the existing model, the target is formulated as churn in the next month. We'll come back to that a little later. Some challenges in churn prediction then. First of all, churn is quite rare. In a healthy company, anything below 5% in monthly churn rates is possible. So this, of course, leads to high class imbalance, and the data scientist has to perform some thought out strategies to mitigate this issue. Then the CRM processes in a global company. So when the salespeople are managing the contracts, there's a lot of manual data entry, which is notoriously dangerous, of course. And also in a global company, the processes related to these contracts can be different and sometimes even uncomparable between the countries. Then another issue is the business assumptions versus data stories. And what I mean by this is that when the business stakeholders approach an analytics team and they request that you create this model with these features because we know they're important, and then the data scientist does that, and then they see quite clearly that the data and the prediction results do not match with the assumption of the business stakeholders, and thus managing this jungle is quite difficult at times. And then lastly, what actually describes churn? What are the events leading to the decision, and how can they be properly modeled using some simple features and data? About the data then, it's time series data consisting of monthly snapshots of these maintenance contracts. So one customer can have multiple contracts, and then one contract usually covers multiple equipment. So the data within contract then is event data of usage, equipment usage, some payment details, and additionally some constant features about contract details and service types, etc. Some specs from the data then, 800,000 contracts in total, ranging from January 2020 to July 2025, with 41 features in total that I grouped for convenience into contract-based, equipment-based, and customer-based features. For the model, I chose to use the CatBoost classification algorithm, which is a gradient-boosted decision tree algorithm. And for evaluation metrics, I mainly used ROC AUC, then Matthews correlation coefficient, and also top decile lift to tell the business stakeholders how we're managing to identify the riskiest contracts. Training, validation, and test sets were created using time-based splits, and then additionally this SHAP value-based feature importance analysis I did. And before any actual improvements, I went over the existing code and the logic of the features and implemented some fixes there as well as some new features. Then I reconstructed a baseline model for comparing the improvements to something. And finally, the actual improvements. Firstly, this time horizon target improvement. So as I said earlier, this churn in the next month is too late for the sales teams to react to. So I reformulated this into this kind of rolling window of churn in the next 6 months. Then another improvement I tested was segmenting the contracts based on their lengths. So the idea out there was that contracts of different lengths most likely have different factors driving churn, and identified 3 groups and created a separate model for each of them. So the short model is for contracts aged under 12 months, then medium model for contracts between 12 and 60 months, and then the long model for contracts over 60 months or 5 years. Then to see if the model choice was a limiting factor for the performance, I tested an alternative model, which was XGBoost. And then lastly, to understand where and why the model still struggles with the predictions, I did some error and uncertainty analysis by using this absolute error in the predicted probability. The key findings then summarized. So for the time horizon experiment, I immediately saw an improvement in the prediction accuracy. So the AUC went up from 0.57 to 0.71. This also gives more reaction time for the sales teams, which was very important, and a slight decrease to the class imbalance, since a churn is now represented by 6 labels rather than just 1. Then for the length segmentation, I saw that for the medium group and the medium model, it achieved the best metrics of all the experiments I did with an AUC of 0.77. From which I concluded that the short and long contracts exhibit some kind of erratic behavior in churn, and they introduced noise into the model that used all of the contracts. Then for the alternative model, the results were very similar to the results with the CatBoost model. So it can be said that the model choice and architecture configurations are not a limiting factor for the performance. And lastly, for the error analysis, there were quite weak signals for the dissatisfaction and churn. And for example, that longer contracts seem to increase the problems in the predictions. Then here are some SHAP B-swarm plots. So these are basically the most important features in order from top to bottom on what affected the prediction. A positive SHAP value means that it increased the likelihood of a positive prediction and vice versa. So this on the left, there is the 6-month time horizon model, and then on the right, there is the medium contract group model. And we see that the features are quite similar. There's around 20 features outside of this list, and they're all the same. And we also see that static features seem to be dominating the models, which is not what we would like, since they're not describing the current events and current levels of satisfaction and dissatisfaction. Then for the error analysis on the left, there's just a general histogram of the predicted probability distributions. So we see quite clearly that the model is more confident at identifying the non-churning contracts, and then not so much for the churning ones. And the two groups are not separated as what like see in the model. And then on the right, there is some results from the error analysis. So after calculating the prediction error, I identified these two groups: large error for where the error was more or equal to 0.8, and then the small error group for less than or equal to 0.2 prediction error. And from there, we see that the three features that describe contract length, which were contract feature 6, 5, and customer feature 3, they all show that for larger values of the features, so longer contracts, the prediction performance is worse. And also from the snapshot month feature, we see that later in the year, it gets more difficult to predict correctly. Finally, the takeaways. So the approach has now been validated thoroughly. The solution now works as best as it can with the given data and the features. The dynamic features do exhibit satisfaction to some extent, which is of course nice. And the fixes I've made are implemented into the production model. Then the data problem, which was a big one for me. The value distributions were quite uninformative, so we encountered a lot of zeros in the values, even for situations where the contracts churned. So there were only quite weak signals of this dissatisfaction, which obviously makes the prediction more difficult. In the future, it seems that there might still be some better features that describe the dissatisfaction and the behavior of leading to churn. So that is still under development. And then the foundational issues of, first of all, predicting human behavior. How can that be modeled with finite data? And then how many of the reasons for churn are outside the available data? And that is all from me. So thank you.